On this upcoming exam, yeah, I think the majority of the points should be this stuff, right? This is where we spent most of our time on. But you don't want to, every question's worth about 10 points. So you don't want to miss these, right? So I say we just start at the beginning and work our way down unless someone has a real urge to work on something else. Now, one last comment that's in my head, then Megan, don't forget what you're going to say. The comment that's in my head is, I don't know if if it works the best, how to approach a problem is my way, I don't know. All I know is, over years, what I found is the easiest and the least to memorize. And that, for me, on this quiz, is just knowing this, figuring out what the total is on your Lewis dot structure. So you figure out the total number of atoms and the total number of lone pair electrons. Whether that's totals 2, whether that totals 3, 4, 5, or 6, right? And then you know how to draw that geometric shape for 3, 4, 5, or 6. That's all I do, right? I just know this one really well. And then I just put stuff around it. The very first column with 0 electron pairs. I just know how to draw that one really well. Then I just add dots on it. That's how I do it. And I think that's worked for me. So I don't know if it'll work for you or not, but it seems the easiest. And then you just look at it and try to figure out the rest. Usually you can. Yes, Megan.
How many questions are going to be in the final?
Oh, the final?
Mm-hmm.
It's going to count as a regular exam, so it can't be too much more or too much less than a regular exam, right?
Just hoping it's not 100 questions.
No, because everything's problem-based. But I think I would expect it to be evenly distributed over the 4 exams. I haven't prepared it yet, but it's really easy. What I do, I just copy-paste, and then I change the numbers. So Bowdy doesn't know the answer is 12. She has to actually do something, right?
Yeah,
I've taken those exams before, where you know what the answer is before you even work it out. Okay, so any other questions on the final or exam 4? No? Okay, so what's the trick to organizing with increasing size? Connor. Just remember what's the biggest. Uh-oh, Connor's in trouble. FR, yeah, not F. Right, so you just draw your arrow down like that. And then you can answer any question. Remember doing that? How about ionization energy, though? Ashley? Ashley says it's the opposite. Do you agree? Paul, do you agree? Yeah, it's the opposite. Because, right, smaller, it's going to be it's tighter, it's tougher to pull an electron out of there. Right? Exact opposite trend. Okay, good deal. 1, 2. Electron configuration. There. And we have our nice little periodic table. Why am I drawing a periodic table, Mia, for electron configurations? Because I'm hoping that you'll talk about what? Yeah, what to fill. So exactly. So here you're filling what? The S's. And then manual. Here you're filling the what? Well, I should write the S's. Oh, not the P's. The D's. Oh, yeah, did you say D? So the D's, because there's 10. And then we're filling Bowdy. How about what's here? The P's. And if you just remember that, the electron configurations aren't bad. You just got to remember what's the difference between all these. We've got complete electron configurations. We've got noble gas core notation, and then we've got valence shell electron configuration. Oh, Rebecca, what is the difference between those 3? They're all electron configurations, but if you give the wrong one, you're going to get it wrong. What's that? Yeah, how do you do this? What's the difference between all these three? It's not an easy, it's a very wordy answer, I would think. Anybody help her out? Choose the closest noble gas, then you go from there. Now, which one of those is that? That's the noble gas core. Right. I think she's exactly right. Choose the nearest noble gas and then go from there. Right? I think we should do one of these. Let's do B and C. A might take too long. But write down your answer for B and C. Let's see if we're all going to agree with this. So Megan, how did you write the noble gas core notation for its tin?
I did KR in brackets, and then 5S2, 4D10, 5P2.
Does everybody agree? Okay. And then there was a trick. Let's say, Steph, let's say all they're asking for is valence shell electron configuration. Take off the D10, good. So don't include that. What would be the answer? And then there's a trick to kind of verify your answer. Do you remember, anyone remember what it was? Yeah, look where? The group number, exactly. Because 10 has a 4 on it. So know your Roman numerals. So you better, your superscripts better add up to be 4. And it does. So that's a check that you should do. Okay. 3. So if you know what you're doing, 3 should be a pretty quick thing to do. Try 3. Yeah, Connor.
Put KR on there again.
No, because you, in the valence, all you want is 4 electrons total. So if you put in, if you added that krypton, man, krypton has 36. You'd be adding way too many electrons. Tellurium. TL is tellurium. That's no, atomic number 81. And all they want is the valence shell electron configuration. All right. If you know what you're doing, it's pretty quick. Why? 6s2, and then, yeah, which p? 6. Yeah, and it has to add up to be 3. So you know that the whole D, forget it. That's not going to be part of your valence. And it has to be 3, so there's your 1, your 6p1. And then 2 more, 6s2. Yeah. Increasing electronegativity. Now there was something else to remember. Alyssa, how does the little arrow go for electronegativity? And it stops where? Perfect. Stops at F. Good. And that can answer any question then, right? No matter what combination I throw at you. All right, now we're at really where all the meat is. Might as well start working these. Did you want to go to the boards, or do you want to just be lazy and stay where you're at? Fine. Next semester, though, might as well bring your exercise shoes. So we are at the best Lewis formula for each molecule. How do you verify it's the best before you go through all this work? What'd they call it?
Vesper.
Yeah, you're going to do Vesper. You're going to do Vesper, yes? Oh, CNOS helps you get the best answer, but how can you verify it's the best answer? Oh, what zero? All
the elements.
What's the word? Starts with an F. All the formal charges. Now, sometimes they can't all be zero. You know they're not all zero, Kendall, when what happens? Like, we want to get the best Lewis formula, so the formal charges are all supposed to be zero. But you could be... Exactly. When there's a charge on this, when it's an ion, you're never going to get all zeros, because all the formal charges have to add up to be the charge, overall charge. So the overall charge on both of these, A and B, is zero. So the best answer that you can get is zero for everything. Right? So try it. Try to get the best Lewis structure for these. And you're right, CNOS helps you get there faster. That's true. But it's not the end game. Formal charge is the end game. Notice how I'm not giving you the equation, Dylan, for formal charge. What was the equation to get formal charge? All right? You got to know it.
You're adding up the sum of
Kenneth, how do you get formal charge of any atom?
It was the formal charge of the atom is valence charge, right?
Formal charge.
It's valence electrons minus the bonds that it has. That would be the electrons left over.
Number of valence electrons.
Minus the number of bonds minus the lone electrons.
Minus the... Yeah, now is it number of pairs or lone electrons? Lone electrons. So you definitely are going to have to know this. How to get the formal charge of any atom. Number of valence electrons minus number of bonds minus number of lone electrons. No, you have to do that structure. Yeah, carbon is in the center for B. If anyone's not sure, just ask. Help you out.
I wasn't sure how to set up just C and the O like that.
There's only 10 though, because carbon has 4, oxygen has 6. So that should be 10 total. Yep.
This was an actually about 1% from D. Since phosphorus has 5 valence electrons, I can't double bond any of these, can I?
Formal charge tells you. Formal charge allows you to double bond anything, anywhere.
Okay.
You just got to calculate formal charge and see if it actually is a good idea or not.
No, is it lone pairs or lone dots?
Dots, lone electrons. 2, 4, 6, 8. You only have 8 electrons. Are there dots on that C or not? Because you only have 2, 4, 6, 8. You have to have 10 total. Right? Because carbon has 4, oxygen has 6. Try it. 2, 4, 6, 2, 4, 6, 8. Now you got 10. Now calculate formal charge of everything and see if you can improve it.
Then is that wrong? If it's 4 and this is 6.
2, 4, 6, 8, 10. You have 11. There you go. Okay, now calculate formal charge of everything. But I can tell right now that you're going to be off because
Yeah.
carbon only has 4 electrons
yeah,
around it.
exactly.
Oxygen has 2, 4, 6, 8, 10. So I would mess with the octet rule before you go through all the work of calculating formal charges. Follow CNOS, follow the octet rule, and that'll really help you get close to the right answer, if not the right answer. You calculate formal charges of everything? 2, 4, 6. You only have 8 electrons, don't you? Or do you have 10? 6, 8. Oh, you have 10. Okay. So carbon is 4 minus 2 minus 2. Oxygen is 6 minus. Now you get 0 for everything. That works. Right? Let me copy your answer. Here's one answer that came up with zeros for everything. Then you had a lone pair on the carbon.
Yeah.
There's one answer that came up with zeros for everything. Is there anyone get another answer? I was just going to guess it's a triple bond. Triple bond.
Oh, no, sorry. I have 4 bonds on it. A 4 bond is I don't know if you can do that.
Oh. Does that work for?
Yeah, it does work though.
Really? It does work. That does work. Right? But, yeah, what's the maximum? 3. The maximum's 3. But formal charge doesn't tell you that, huh? But yeah. I never saw that before. I never even thought of it. Surprised no one's said it in 15 years of teaching. So that's the only possibility is this one, huh? Yeah. Try B as in boy. Carbon's in the center. Connor, what did you get as an answer for this one?
0.
So everything gets to be 0 that way?
Yeah.
Connections 2. Yeah, that does work. I'm copying Connor's here. Then there's a lone pair on the end?
Yeah.
And then, and this guy has all his. 5, 16, no, 2, 4, 6, 8, 10, 12, 14. Yeah, that works, 16. And then the valence on everything. Yeah. I think this works. Are there any other answers besides this one? What's another one?
There's only 2 single bonds.
2 single bonds. That works? And then what?
There's 1 lone pair of carbon, and 3 lone pairs on Br, and 2 lone pairs on
2, 4, 6, 8, 2, 4, 6, 8, 10, 12. There's 16. That works. And then bromine's 0. 2, 4 minus, yeah, that's 0. Wow, that works too, don't it? Okay. What does the answer, before you even do, Emily, number 6, what does the answer look like? What is, what, at least I have a picture in my head. Resonance descriptions. I have a picture in my head what the final answer is going to look like. What are you drawing? They say resonance descriptions. They want, you have all these different structures, and then you have what in between. These little arrows, right? And then usually they have brackets too around whatever they're drawing. Do you remember this? When I see the word resonance description, right away I'm thinking of doing this kind of thing. Right? I'm drawing little brackets.
Oh, okay.
Remember doing this? That's what I think of when I think of resonance description. So I don't know how many there are, but this is the idea. So try it. Right? When they say resonance description, this is what they're talking about.
We're still doing C-notes on this one.
So you always do C-nots to try to get the best answer.
No, could we do a double bond with that?
Try it. You do, formal charge will tell you whether it's a good idea or not. But remember with resonance, you want to move this double bond around. And it's always moved around between identical atoms. So if you move a double bond with an F and then move it around with the 2 O's, you're going to have a different structure because double bond is shorter. So you pretty much just want to move it with the 2 O's. Move that double bond around. So I think there's only going to be 2 answers and not 3. Right? Because there's only 2 identical O's. So I think an appropriate answer here is just going to have two resonance descriptions, 2 structures. There won't be 3. And CNOS and formal charge, all that helps you get where you need to go. Oh, N's in the center. What am I doing? Because N's in the center. Oh, it even says N is the central atom. Betcha. There. Let's not do it yet. So there's 24. So there's the starting point, right? And then pretty much just erase a lone pair, make it a double bond, draw another structure by erasing the other lone pair on the second oxygen, making a double bond. Okay. So when I see resonance description, make your life easy. Think of it. Think of, oh, I'm going to have to draw these structures with a double arrow in between. And then that double bond you're moving around is always between identical elements in that molecule. Right? Oh, and then finish off the fluorine. There's your 2. So you don't draw one with the F. Here's where this is everything. Everything's on here. So draw your best Lewis formula. Find all the formal charges. Draw a nice 3D structure of that molecule. Identify the electron pair arrangement. The name of the electron pair arrangement, which just corresponds to the total number of surrounding atoms and lone pairs. The molecular shape, now you have to take into account lone pairs. Hybridization, remember the superscripts have to add up to be the total. And then dipole moment, see if all of the electronegativities cancel out in your 3D structure.
This is one, like with S, since it has 6 electrons, it's going to double bond each of these out.
Well, if you do formal charge on S, it's going to be...
Like, it'll still be 0, because S minus the neutron.
Oh, that's true. But then look at the oxygens.
Yeah, the
You
oxygen.
just calculate the formal charge on the oxygens.
Yeah, that'll still be good, because it'll be 4 plus.
Oh, you didn't have them all on there.
Oh, I don't, because I had to make sure that, like, I wanted to make sure this looked
What?
right. Okay.
4 times 6. You have 24 total?
Hold on. 2, 4, 6, 8, 10, 12, 13. Wait, not 13, 14, 16.
Yeah.
Yeah, it's 24.
That should work, right?
Okay. I just had to make sure, because, like...
That should work.
How for these the angle bonds, they're incorrect. How are these? How are we supposed to draw them?
Oh.
The resonance description.
We weren't worried about that. Whoever I had helping me grade this stuff shouldn't have been taking points off here. We weren't worried about it. So I can fix that. I'll give you 6 points. All right.
Is it dipole or dipole? It's dipole. I told you. I would say dipole. You said it was the SP thing?
And remember the general rule. The general rule is find all the valence, make octets on everything surrounding, put anything left over on the center atom. And that pretty much covers your tail for everything. So if each fluorine has 8, 5 times 8 is 40. Got 2 left over, so they have to go on the center atom. And then how I do it, I see what the total is, and I draw that total 3D structure as nice as I can. Then I go from there. And my total here is going to be 6. Because the total is going to be the number of surrounding atoms plus the number of lone pairs on the center atom. So it's the total number of things that are surrounding that center atom. Lone pairs and atoms. So that has to be 6. And for the 6, remember that's the guy who has a square in the center where 2 are going back and 2 are going forward, right? And then it had a top and a bottom. Had a square in the center, and then had a top and a bottom. Okay? And then, this is just where I start. So no matter what my Lewis dot structure looks like, I figure out what the total is, and then I draw this shape. And then I try to figure out things from there. Yeah, so if I put my lone pair anywhere I want, I'll get the same answer. But it's kind of easiest to see if I put it up on top, right? Or on bottom. Then I have my F's.
Do we have to put the F?
Yes.
Oh, we do. And if we don't,
If you don't, it'll be wrong. So now you have electron pair arrangement. You have molecular shape. You have hybridization. We had dipole moment. So electron pair arrangement, everybody is octahedral or square bipyramidal. Either one works. It's the name that corresponds to the total. Molecular shape? Square pyramidal. Hybridization? Add up your superscripts so they add up to be 6. S maxes out at 1. P maxes out at 3. So I need 2. Perfect. Does it have a dipole moment?
No. Oh, yes.
Yes.
Do you have to put the 1 if you were just leave it as S?
No. I kind of like putting the 1 because it makes more sense. So have a good day.